Section 6.5, using a normal approximation for binomial distribution problems. Now we use binomial distributions when we want to make inferences about the true proportion P of successes in a population. When we're talking about making inferences, it's talking about using the results of a sample to make some kind of estimate or conclusion about an entire population. So let's say we have a big box of USB drives. We randomly select 10 drives from a shipment of 10,000. And in the whole population of 10,000 drives, 200 of them are defective. They're bad drives. X is going to equal the number of bad flash drives in our sample of 10. And this isn't quite binomial because it doesn't meet the independent condition. So it starts off with 200 out of 10,000 being bad. Once we pick one, whether it's bad or not, both those numbers, or at least the bottom, is going to change. Okay, and that probability of selecting a bad one changes with it. So these are not independent because each selection changes the probability of the next being bad. The problem is that in almost every situation where we're taking a sample from a population, we're going to encounter that same problem. Generally speaking, when we take a simple random sample from a population and we choose someone or something, we don't want to be able to choose it again. In other words, we're sampling without replacement. And because we're sampling without replacement, that's changing the probabilities. It's changing the denominator of that fraction every time we pick someone. So these results are not independent of each other. And that violates the I condition in bins, which means it's technically not a binomial setting. However, there's a workaround. If we have a sample size that's relatively small compared to the population, we can use that to justify that condition. So what's relatively small? It's anything where n is the size of the sample, is less than 10% of the population size, capital N for a population. So as long as our sample is less than 10% of the population, we can ignore the fact that we're sampling without replacement and changing the denominator of that fraction. Those changes are going to be negligible with that size sample. So if we have 10,000 flash drives, as long as we're sampling 999 or less, we'll be able to say we can ignore the fact that they're not actually independent. Now, in the last section, we talked about what binomial distributions look like and how when we have a small p, we get something that's skewed to the right. And it's because our sample size is small. Most of the time, we're going to get a small number of successes in our sample. It's going to be the opposite if we have a p that's fairly large, okay, with a small sample. In this case, we'll get mostly a large number of successes. It's only when we have a p that's close to 0.5, right, that we'll have something that's approximately normal. Again, this is all for small sample sizes. So in the problem that we were just dealing with, 200 out of 10,000 flash drives were bad. That's a p of 0.02. Okay, so it's way more skewed than this one. This is what it'll look like with a sample size of 10. We can see that it's clearly and dramatically skewed to the right there. Now, the whole goal in this section is to be able to apply a normal distribution to a binomial setting, or an approximately binomial setting. So let's look at what happens when that sample size increases. So in these three graphs here, we have the same p. It's 0.8. Okay, we had seen it on the other graph. It was more skewed than it was in this one, and that's because the sample size was smaller on the other graph, on the other slide. It was n equals 5. We double it, and we can see it's a little less skewed, and then we double it again. All right, we can see it's even less skewed. It's starting to look a little more normal, and then we bump it up to 50, and we can see it's taken on that normal distribution. So something that started as skewed to the left, as we increase our sample size, it becomes more and more normally distributed. So when it comes to approximating binomial distributions with a normal approximation, we're going to be able to use a normal curve to model this distribution as long as our sample size is large enough. Okay, and large enough depends on the value of p. The farther p is from 0.5, the larger the sample size needs to be. We can verify this condition mathematically with what's called the large counts condition. I'm going to refer to this as the success-fail condition. We're going to take our sample size, we're going to multiply it times the probability of success, and then we're going to do it again for the probability of failure to see how many successes and how many failures we expect to get in a sample. If both of these values are greater than or equal to 10, we can use a normal distribution to model the problem that we're looking at. So let's take a look at this example here. Suppose that exactly 12% of teens aged 14 to 18 have debit cards. The random variable x equals the number of teens who have debit cards in a random sample of 500 14 to 18-year-olds has close to a binomial distribution with sample size 500 and p equals 0.12. To start, we want to see, can we use a normal distribution to model this instead of using a binomial distribution? So to check whether or not we can use a normal distribution, we're going to check those two conditions that we just went over. So to start, is our sample size, n, less than 10% of the population size, which we use capital N for? So we have a sample size of 500. This is talking about teenagers aged 14 to 18 in the United States, and 500 is less than 10% of all US teenagers in that age range. So far that is met. We'll continue. The other one is the success-fail condition or the large counts condition. So we're going to take our sample size and our probability of success, and we're going to multiply them to see, do we get something bigger than 10? And we do. Okay, we do the same thing, except instead of NP for this next one, we're going to do N times Q, whereas the book likes to write it N times 1 minus P. Okay, we get something that's bigger than 10 again, so this one is also met. And because those two conditions are met, we can use a distribution that's approximately normal to solve this problem. So part B, let's find the mean and the standard deviation of this approximately normal distribution. Since it's approximately binomial, we can use our two equations from earlier in the chapter. The mean is N times P. The standard deviation is radical NPQ. So we get a mean of 60 and a standard deviation of 7.266. Now part C asks, what's the probability that at most 50 teens in the sample have debit cards? Let's think about this for a second. If we were doing it with a binomial distribution, we would have to add up all the probabilities from 0 up to 50. Okay, and that would be the short way, because the other ones that aren't included here are 51 up to 500. So that would be a whole bunch of equations to plug into and add up. That's way more work than we want to do. So instead of using a binomial distribution, we're going to use this normal distribution. And we'll put right in the middle there the mean that we got on the last slide, 60, with a standard deviation of that 7.266. What's the probability that we get at most 50? Draw that boundary, shade it in the appropriate direction, and now we're going to find a z-score. Okay, remember the mean always comes after that minus sign. This z-score should be negative because this value is to the left of the mean. Once we get that z-score, we look it up in our table, and we get our answer 0.0844. Remember, if we're looking for the area to the right of some value, once we find it in our table, we'd have to do 1 minus. But since this one is to the left, this will be our selection.